This is another way we can use the definition of tangent plane. Take a look at this problem below. It says find a normal vector and a tangent vector at a point P. So that P could be our P naught. And we have our function here. And if I solve this for z, which I will, because I want you to see how that looks, and that makes this a little bit strange how that works out for us. So if I solve this for z, first thing I do is move the 3 over. Okay, that's no big deal to us. Now we're going to divide by e to the x squared minus y squared both sides. So it's going to be e to the x squared minus y squared both sides. And some of you will be okay with this, others will be like, what do I do now? Actually, this actually turns out to be pretty nice. So I'll end up with, I'll just write it to the right here. This is going to be z equals, now keep in mind here, when I have an e on the bottom, that exponent could be a negative and I can write it in the numerator. So this is really 3 to the e negative x squared minus y squared. And I can simplify it a little more now because this is really 3e to the negative x squared plus y squared. So a little bit of algebra acrobatics here. So now we got it to the place where we had the previous problem at, and we can find zx. You can call it zx as well. That means I'm looking for the partial derivative with respect to x of z. And that would be the derivative of e to the x is e to the x, so I just write it out. And remember, constants just go along for the ride. That's why the 3 is just sitting there. Times the derivative of the inside, and this is with respect to x. So I only have to worry about this piece. This here is a constant. Okay, so that's going to be negative 2x. So now that actually equals negative 6x e to the negative x squared plus y squared. So there's my zx. Now I'm plugging in the point 2, 2, 3. Now remember, for this process, I won't need the z, because look at my formula here. It's x naught, y naught. So the z doesn't play a role. The z plays a role in the end, and my z is actually 3 for this piece. So we'll worry about that later. So then that implies when I plug all that in, and I'll write it formally here. So f of 2, 2. And that's going to result in, which this equals negative 12 e to the, and that's going to give me a 0 there, which equals negative 12. So I'm going to do the same thing with the zy here. And you'll see why I'm doing this in a minute. What we're actually doing right now is we're finding the normal vector to the surface. And the surface meaning this surface here. Okay, so my zy is three e to the negative x squared plus y squared times 2y. So that equals 6y e to the negative x squared plus y squared. And then when I plug in, oh, I should have an x there. So this should be an f of y, and that's going to equal, I'm just going to plug in 2, 2 for that. Actually, let me put that in too, just to be formal here, which this equals 12. So what happens here then is, if we think about what we've seen in the last video, if you remember it, remember me moving this z over really results in my normal vector to the plane, and remember that normal vector is my direction. So this fx, fy are my x and my y, and my z, when I move it over, is going to give me that negative 1. So actually my normal vector here would be negative 12. Oops, let me fix that 12. 12, negative 1. So right away I get the normal vector just from understanding the formula. So now we're going to talk about the tangent vector. And to get the tangent vector, that's pretty easy too. Because think about this, the tangent vector is going to be orthogonal to the normal vector. And this is just kind of going back to understand the dynamics of the tangent vector and the normal vector here. So the cool thing about that then is if I find a vector that's orthogonal, it's going to be a tangent vector. So that's the beauty of that. So for that, I'm just going to play around with this. And if I can find where that dot product is 0, then I found a vector that's orthogonal to n. So that means by understanding that tangent and normal vectors are orthogonal to each other means I just got to find a dot product, a vector where the dot product is 0. So for that n, I got negative 12, 12, negative 1, dotted. And let's see, I can put a 1 here. I could put a negative 1 here, and I could put a 0 there. And all I was doing here was taking a look at, oh, hang on, did I do that wrong? Yes, I did. Actually, make that a positive 1. Now it works. Because I understand what dot product does, it multiplies component-wise, and then I add them. So negative 12 times 1 is negative 12, plus 12 times 1, which is 12, and then negative 1 times 0 is 0. And again, that's all I'm doing here with dot product is just adding them. So that's going to give me 0. And when the dot product is 0, those vectors are orthogonal, which means since this is a normal vector here, that the one I found is a tangent vector. So that tangent vector then, I don't know what to call it. I'll call it T. That's fair. It's not really big T though, because that would imply it's a unit vector. We don't get that here necessarily. So this is going to be 1, 1, 0. And honestly, there's infinitely many of these, so everyone could get a different answer and be right. So that's this problem here. And that's what's nice. We're using the idea of tangent plane to actually do part of this problem, the normal vector. So pretty cool.